Welcome to class students. In this class we are going to continue our discussion on useful system tasks. Hierarchy at any level can be displayed by means of the %m option in any of the display tasks, $display, $write task, $monitor or $stroke task, as discussed briefly in section hierarchical names. This is very useful option. For example, when multiple instances of a module execute the same Verilog code, the %m option will distinguish from which module instance the output is coming. No argument is needed for the %m option in the display tasks. Displaying hierarchy information. Module M. So we are observing partial code and we are analyzing. So module name is module M, initial $display, displaying in %m, and module. So one more module is there, module top, instantiate module M in this module top. So M, there are two instances, M1, M2 and M3. So in M1 you are displaying, M is a module name, so you are creating three instances, M1, M2 and M3, and you are displaying hierarchy. So when M1 instance is called, so you are displaying, so in module M you have got displaying in %m, it will show the path. So displaying in top dot M1, so top is a one more module name, M1 is instance name. So here when you call first statement M space M1, so first instance M1 is called, so it will displaying in top dot M1, displaying in top dot M2, top dot M3. So it will display the hierarchy. So this will be top level module. In that this will act as a module instance. Three instances are created, M1, M2, M3. So that hierarchy will be top dot M1, top dot M2, top dot M3. So module M, three instances are created. This feature can display full hierarchical names including module instances, tasks, functions and named blocks. Strobing. Strobing is done with the system task keyword $strobe. This task is very similar to the $display task except for slight difference. In many other statements are executed in the same time unit as the $display task. The order in which the statements and the $display task are executed is non-deterministic. If $strobe is used, it is always executed after all other assignment statements in the same time unit have executed. Thus, $strobe provides a synchronization mechanism to ensure that data is displayed only after all other assignment statements which change the data in that time step have executed. If you consider an example, always at positive edge of the clock, begin, there are two statements in this always block, so begin and end, A equal to B, C equal to D. One more always statement at positive edge of the clock, $strobe displaying A %B, C, A and C value in binary you are displaying. So observe that instead of $display we are using $strobe. Since only one statement, we are not writing begin and end here for second always statement. In this example, the values at positive edge of the clock will be displayed only after statements A equal to B and C equal to D execute. The $display was used. $display might execute before statements A equal to B and C equal to D, thus displaying different values. $strobe will ensure that these two statements are executed. A will get the value of B, C will get the value of D, and those values after assigning those values, so $strobe will display the values of A and C. A random number generation. Random number generation capabilities are required for generating a random set of test vectors. Random testing is important because it often catches hidden bugs in the design. Random vector generation is also used in performance analysis of chip architectures. The system task $random is used for generating a random number. $random seed. The value of seed is optional and is used to ensure the same random number sequence each time the test is run. The seed parameter can either be a register, integer or time variable. The task $random returns a 32-bit signed integer. All bits, bit selects or part selects of the 32-bit random number can be used. Generate random numbers and apply them to a simple ROM, read-only memory. So module test integer are seed, register 32-bit, address and data 32-bit. So address and data both are of size 32-bit here. So 32-bit address line means each can have 32-bit address, that many location 2 raised to 32 different locations available. ROM instance name is ROM1, data and address. Initial R seed value we are initializing it to 2 to make sure that whenever you execute this program again and again, so you will get same random number need to be generated. In that case seed value is used. So here R seed is 2. Arbitrarily define the seed as 2, some random value. So we have initialized with 2. Always add pause edge of clock address equal to $random R seed generates random numbers. End module. The random number generator is able to generate signed integers. Therefore, depending on the way the $random task is used, it can generate positive or negative integers. If you consider an example, generation of positive and negative numbers by $random task. Register 23 down to 0, random 1 and one more random number 2. So 1 and 2 variables are defined, each of size 24-bit. Random 1 $random modulus operator 60. So this will generate a random number between -59 and 59. So if you use the second random number 2, you are assigning a concatenation operator, addition of concatenation operator to $random, then modulus operator 60. This $random generates a positive value between 0 and 59. Note that the algorithm used by $random is standardized. Therefore, the same simulation test run on different simulators will generate consistent random patterns for the same seed value. Initializing memory from file. Verilog provides a very useful system task to initialize memories from a data file. Two tasks are provided to read numbers in binary or hexadecimal format. Keywords $read memory mem_b and $read mem_h are used to initialize memories. $read memory b file name, then memory name. Read memory b file name, then memory name, starting address. Read memory b, so then various formats we can use this read memory system task $read memory b file name, memory name, start address and finish address. Similarly, identical syntax for read memory h also. So you can give file name and memory name, memory name, start address as well as finish address. In 3 different formats we can use read memory h also. The file name and memory name are mandatory. Start address and finish address are optional. Defaults are start index of memory array for start address and end of the data file or memory for finish address. Next example illustrates how memory is initialized. Module test. So here you are defining 7 down to 0, 8 bit. Such an array of memory you are defining 0 to 7. So 8 locations each of size 8 bit. 8 locations each of size 8 bit we are defining. So we can say 8 locations 8 bit 1 byte. So total 8 byte memory is declared by this. Already you have seen in studying vectors and arrays, how to declare arrays of multiple bit size. So this is an array of 8 locations of multiple bit width, that is 8 bit here. Integer I, initial, begin. So in initial statement you are using read memory from the file name init.data. DAT. So from notepad you are saving that data and that data you want to collect, and the memory name given is say memory. So module test display contents for initialized memory. For I equal to 0, I less than 8, so total 0 to 7 locations. Each time we are incrementing memory location and we are displaying see the content stored in memory in binary. So I will act as an index starting from 0 to 7, and memory I will be you are pointing to the value that is stored in file init.data. So you are displaying contents of initialized memory with the help of this for loop. The file init.data contains initialization data. Addresses are specified in the data file with @address. Addresses are specified as hexadecimal numbers. Data is separated by white spaces. Data can contain X or Z. Uninitialized locations default to X. A sample file init.data is shown below. At address 002 you have got so 8 ones 01 8 bit, then all zeros 8 bit, 1 0 8 bit. So 2 3 4 5. At 6 you have got 4 ones, then Z. So these 8 bit data, 4 zeros followed by 4 ones, 8 bits grouped together. When the test module is simulated, we will get the following output. Memory 0. So memory 0 and memory 1 are not defined. So those locations will be loaded with default value X. Memory 2 to 5. So these values are displayed. Then 6 and 7. These values are displaced. In this case, you can observe memory location 0 and 1 are not defined. Those are uninitialized and default values are X. Thank you, students. We will continue in next class.